Hi everybody. So in this recording, I will discuss so-called deductive methods for verification, and then shortly synthesis in hybrid systems. And why we look into hybrid systems we discussed in an earlier recording, where we said that hybrid systems models offer a suitable framework to characterize a number of, or maybe even all cyber-physical systems and autonomous systems and other systems of interest. And the naming of the deductive methods will become clearer later on in the talk. So I will mildly refer to this simple hybrid system model where we have the state space, and the state space is partitioned into multiple regions, and each region corresponds to a mode of the system. There is vector field, but the vector field it may change depending on where we are. For example, where we might follow certain dynamics in this region, and it may it refers to this F1 indexed, or maybe we should index it with F alpha 1, because it seems like in this notation we call the mode as alpha 1, and it is active only in this region that corresponds to the to that mode, characterized by the invariant that essentially maps the label of the region to the subset of the continuous state space where that dynamics that vector field F alpha 1 is active. And not surprisingly, as we change the mode, we go to a different region where some other invariant is active, and now the dynamics becomes F alpha 3, a function of the state and the control inputs. And there might be generalizations of this. Hybrid systems come in very many different ways and flavors, but just this is one simple model that I will be sometimes referring to. Okay, so this is the model that we will be using, and in addition to the in addition to the evolution of the dynamics following these vector fields, we also keep track of from what mode to a different mode we are jumping, as depicted in this with this little arrow here. Okay, so it allows for changes in the modes, and as the modes change, how the system underlying continuous dynamics evolve changes. Okay, so let's remember this one. And then we said there are many different approaches for verification and synthesis for hybrid system models, and one of the main characteristics that differ this class of models from those that we study more heavily conventionally in formal methods is that for hybrid systems, because of the existence of continuous state spaces, exhaustive search is not possible. So model checking or reactive synthesis or anything that relies on finite state representations will not be directly applicable. And I already covered quite a bit on this first approach, where we essentially take the underlying continuous state space and discretize it into finitely many states and try to approximate the underlying continuous evolution by a finite state model. And we use that for synthesis purposes. In this recording, I'm going to look into these deductive techniques, and as I said before, I will not cover much about these explicit construction of the reachable sets and keeping track of where the system might go and whether it might get into trouble. Okay, so when we want to talk about verification or synthesis, one of the first things that we need to clear is perhaps what specifications, what is the purpose of it. And I'm going to discuss a couple of specifications that will become useful, and I will grow this later to more general subsets of temporal logic, like statements or continuous state spaces. Obviously, that statement needs to be made clearer. So we have this hybrid system model. Sorry. we have the hybrid system model given here, and this notation is going to represent the solution of the underlying dynamics at time t, starting from the initial condition x is 0, and the initial condition may represent the initial mod and the initial state, but for the given simple model, if we fix the initial condition for the continuous state space, it also determines the initial mode, so there's a little bit of simplification there. Not that it is too important. So one of the temporal properties that controls has been studying pretty heavily is stability. And for that, we have an equilibrium condition or some fixed solution of the underlying differential equations. And then we start from some initial condition, or it could belong to some subset of the state space. And we are interested in whether all solutions that start from the set of initial conditions will converge to the equilibrium condition, or that fixed solution as time grows. So that's the stability. And safety roughly can be characterized as given some unsafe set, there's a set of subset of the states that we don't want to enter. For example, this set here, we are starting from x0. The question is whether we will call the system safe if there exists no time, it is called t unsafe here, such that the initial conditions, the solutions with initial conditions in the set x0 enter the unsafe set at time t unsafe. So this roughly saying that there is no initial condition and there is no finite time within which the system will start from this green set and will go and enter the red set. Reachability is now there is a point that there's a set that we are not necessarily trying to avoid, we want to enter it, and the reachability looks into the question whether there is one solution that starts from x0 and it will do something and it will reach, it will come to x sub reach within a certain amount of time that we call t sub reach in this characterization. And it's just going to grow. Eventuality essentially is whether reachability holds for all initial conditions in the initial set, and we can combine these properties and write relatively complicated specifications. For example, if we have 3 sets, we might look into starting from some set, whether we will reach 2 other sets, but we would not want to enter one region without first going through some other region, and all sorts of combinations as possible. And it is going to build up toward the type of properties, at least the way that we hear them, that we encounter in subsets of temporal logic. And we will get to that. Okay, so we will look into these specifications, and or these are typical specifications that we encounter in more conventional studies of study on deductive methods for hybrid systems or dynamical systems. And if I'm not mistaken, in these slides, I will refer to the safety property more often than the others. Okay, so what does a deductive method do? This is going to be for verification purposes, and then I'm going to have a few comments for synthesis, generalization to synthesis. So if you remember, the safety property holds for, and I'm going to look into just a pure continuous dynamics. There are no modes in this, and I will point out to the distinction between purely continuous dynamics and hybrid dynamics in the next slide. So if you remember, we will call the system to hold the safety property if there exists no time t and no trajectory such that starting from x0 within that time t we enter the unsafe set and we stay inside the state space. So we want to check this property whether for a given dynamical system this property holds or not. And deductive methods do not necessarily try to directly answer that question. Instead, they try to check something related. And one example here is that we will try to check if there exists a differentiable function b. B is from the state space where x lives to reals. And it is going to have a few properties. In the initial set, we want this thing to be b to be less than or equal to 0. And in the unsafe set, x sub u in this slide, we want b to be greater than 0. And everywhere in the state space, everywhere we want b dot to be less than or equal to 0. That means if b starts less than or equal to 0, since its derivative along the trajectories, b dot is the gradient of the gradient of b with respect to x times the vector fields. So it is the rate of change in b along the trajectories of the dynamics, right? Following the trajectories of the dynamics, this b cannot start less than or equal to 0 and ever become greater than 0, right? Strictly greater than 0. That's going to mean if I start somewhere in this, I am less than or equal to 0, I cannot grow, hence I cannot enter this region ever, right? I can leave it, I can wander around, but I can never enter this unsafe region. Then obviously, if we can somehow verify that this statement holds, if we can find such a function b, then it's going to imply that the safety property holds, right? And therefore we can call, if we can find such a function b, we can call that to witness the safety property for this underlying dynamical system for given sets x0 and xu, etc. And there, depending on what property we try to verify and what kind of a function we try to construct, there are different names for these functions. And for this particular case, it is typically called a barrier certificate, because essentially the function is less than 0 here, greater than 0 here. There's a sub-level set of the function b is equal to 0 along the trajectories of the system. We can never cross across the b equal to 0. Therefore, that is a barrier between the initial set of states and the unsafe set of states. So if we can find b, then fine, we will have solved our verification problem. And if we cannot find such a b, then we cannot say much, because this arrow is only one directional. There is we don't have this direction. Okay, and actually we haven't even spoken about how we ever can go and algorithmically search for a function like this. So I'm going to quickly go through now the flow, a typical flow for search for a barrier certificate or a search for algebraic witnesses, algebraic functions that witness the specifications against dynamical systems through deductive methods. So we want to answer a question whether a given system is safe or not. That's the starting point. And we say, no, we cannot answer that, but we say, if we can find, so we want to answer this question, but if we say that's too hard, I'm not going to try to answer that. Instead, I'm going to go and look for a function b that satisfies certain properties. And the point is that if we can answer this, then there is this one-sided implication. But typically searching for a general class, for a function from a general class of functions that satisfies certain properties is hard, then we will say, look, that's too hard for me. Let's go and change that question a little bit, all right? And instead of going and imposing b is less than 0 for all x in some set, we will say that, you know what, let me actually relax that condition, and instead of looking for a function that satisfies those, I'm going to look for a function that is minus b minus some positive some other function is that is positive, non-negative, and I am going to represent this set x0 through some inequalities. For example, the set of states x that are in x0 is going to be represented by this function g sub 0, and the set x0 is going to be the set of states or set of points for which g of 0 is greater than 0. So for each set that we encounter for x sub u and x, etc., we'll go and represent them through these inequalities over on given functions. So then the point is, if we can go and find if we can go and verify whether this statement holds or not, that's a witness for this statement. And then obviously we will have this implication as well. Typically that's even hard. Then we say, you know what, searching through general families of functions is hard. I'm going to go and search for over some polynomials of certain degree. All right, I'm going to look for this B within the polynomials up to some degree, quadratics, fourth order polynomials, whatever. So, and obviously that this is not equivalent to this one, but there is a one-sided implication. If I can find such polynomials, that's going to be an indication that some function exists, etc., but not the other way around. If there's no polynomial that satisfies given conditions, there might still be functions from a more general family of functions that might satisfy the conditions I cared about in this box. And then the story goes on like that. So, okay, polynomials, but these are now inequalities over polynomials, a hard question to answer. You may relax that as well and go ahead and impose so-called sum of squares optimization or some other forms of semi-definite programming, typically that more conventionally we run into these things, but it doesn't have to be that. So somehow you actually relax even further so that there is a decision procedure that we can apply to search for these witnesses. And where if we cannot answer this question, this very final question that we are intending to answer, it does not say much about whether the actual question that we wanted to answer through deductive verification was answerable or not. We might have lost this thing any point in this flow because every step we are actually making the search more restrictive, more restrictive, more restrictive. And if we cannot answer this point, then we can ask whether we could have done anything better for this one-sided implication, for this one-sided implication, for this one-sided, for this one-sided implication or not. And we can later discuss what that means. So deductive verification techniques, if you can create a positive affirmative answer, that's good. If you cannot, then you need to go and look into the steps that you have taken and try to see where things might have gone wrong. And obviously one of the explanations is that indeed this question did not have an affirmative answer, but except for very special cases where all these one-sided implications are actually indeed two-sided, and they are very rare cases in which that happens. Unless you are in one of those cases, then it becomes a little bit of trial and error. So we can even call that the non-affirmative answer is inconclusive in these deductive techniques. Okay, so that is the general flow. The question that you might want to answer could change. The sufficient condition that you invoke might change. The way that you actually parameterize and deal with things might change, and the way that you try to solve, instead of using semi-definite programming, we might go and use a different decision procedure, but this is roughly the general flow. So how do things change when we have hybrid dynamics? And on the left, I'm repeating what we had in the previous slide, and on the right, I am showing just one instance where things will be different. So we are imposing these conditions on the function b. The first one for all states in x0, the second one for all states in xu, etc. Now for each mode, we will introduce one of these barrier certificates. Appropriately smooth functions for each mode, and then we will go and impose similar conditions. We want the b to be less than or equal to 0, but we want the b sub l. Within the mode L, we want that function to be less than or equal to 0, and then that not for all x in x0, but we take the intersection with the set of states where that mode is active. So if x0 is in this a set like that, and then for the first one, b sub alpha 1, we want b sub alpha 1 to be less than or equal to 0 only in this part, not the entire x0. And the story goes on like that. The second condition was on x sub u, and now we restrict it to be within the mode and x sub u. Similarly, this derivative condition is in the same way. And then we have one more restriction on these things, which is if we ever jump from mode L to L prime, if there is a mode switch from L to L prime, within which when that happens, if for whatever reason a discrete jump on x0 also happens, we want the b to be decreasing or non-increasing across those jumps as well. So let's say there is no jump, we have a smooth transition through this point up until this point. B sub alpha 1 was active, and then right after that point, B sub alpha 3 becomes active. So we don't want the value of in B from B sub alpha 1 to B sub alpha 3 to jump. All right, we don't want that to increase, and this last condition takes care of these discrete transitions. And this is typically how these more control theoretic techniques actually keep track of the discrete jumps in the dynamics. And you can imagine if there are many of these discrete jumps possible, then these conditions will become pretty complicated. Okay, so this is the idea behind deductive verification. How do we use these things for synthesis? Let me go back first. So instead of having, synthesis is going to refer to in this context, instead of having this, I'm going to have x dot is equal to f of x and u. And I'm going to ask, you know what? Can I find some control signal u that's going to keep me safe, right? Hence, we can take all these things, and in addition to what conditions we have, we can go and qualify whether there exists some signal u that is going to make all these conditions hold. And you can try it. Conceptually, that approach is going to go through, and there are lots of papers that try to do that and try to pull different tricks to make these resulting conditions a little bit more manageable. I'm going to refer to that as looking directly into synthesis through deductive methods. Conceptually, there's nothing wrong, but computationally, even the verification problems are relatively complicated. So that approach becomes even more computationally demanding. And then there are lots of different ways of using these ideas indirectly, the verification ideas indirectly. One of them is called so-called control Lyapunov functions. And the dynamics are given in this control affine form. And then it reads as if there exists a function v, similar to the various certificates, but in this case, we are concerned, in this one example, little example here, we are concerned with the stability of the dynamics of the system. And the question we are asking is whether we can find a control signal u that is going to stabilize the dynamics around equilibrium at x equal to 0. Then the sufficient condition reads as, if there exists a function v that, along with some other technical conditions, satisfies this statement. We want the partial derivative of v with respect to x times g, this part of the dynamics, to be equal to 0 at all points that are not equal to 0, that is not an equilibrium point. We want that thing to imply that the partial derivative of v with respect to x along the direction of f of x to be less than 0. So whenever this thing vanishes roughly, we want this thing to be less than 0. If we can find a v that satisfies this condition, then we can actually construct a controller from the knowledge of v. We can construct a stabilizing controller. We can take that controller, plug it into here, and then we will have a proof that actually these dynamics the closed-loop dynamics will be stable around the equilibrium point. And if you look at this one, through some tricks, we can see that actually this does not necessarily refer to the control input u directly. Control Lyapunov functions figure out a relation between the derivative of v with respect to x in the direction of f and in the direction of g such that if the function v satisfies that relation, then we can find a control signal u out of the knowledge of v that's going to stabilize the system. So that obviously makes the problem easier than directly explicitly introducing the u into the algebraic conditions that we have and qualifying those statements with respect to the existence of the control signal u. Another approach to that relies on deductive methods probably is a little bit more indirect. I did not know what to call it. I call it indirect methods, but essentially, to a certain extent, ignoring the underlying dynamics. These methods typically find a nominal trajectory that satisfies the high-level requirements that you might have in mind. And then they ask the question of, if I ever find myself not along those nominal trajectory, can I solve a more localized and hopefully a simpler verification question, which is, if my system starts from this point, am I going to go and get and approach this nominal trajectory that I want to follow? And you may ask it from many different conditions. So do I have a controller? The controller has already been designed, or you can rely on simple control techniques for linear systems and ask the question, if I use a given controller or a controller that is designed for the linearization of dynamics along this nominal trajectory, and if I find myself away from this nominal trajectory that I want to follow, am I going to go back to this nominal trajectory? And obviously you try to cover through a bunch of questions as much space around your nominal trajectory as you can, so that if you ever find yourself off the nominal trajectory, you'll try to go back to that, and doing that, you will be able to satisfy the high-level requirements that you had in mind. And the nominal trajectory, remember, was chosen with those high-level requirements that you wanted to satisfy. So that this is essentially, there is no direct synthesis per se using a deductive method here, but somehow you come up with something that you want to follow, and you try to use the deductive techniques to certify that your closed-loop dynamics will be able to follow that. And that is going to be a transition to a little bit more, this is a transition point where how we can actually go and introduce more temporal logic type specifications. And I am not going to get into details of this, but let me at least set up the problem. So we have continuous dynamics, not necessarily now hybrid dynamics with mode switchings, etc. We will end up having a hybrid dynamical system, but for a different reason. So we have that. Then we introduce this labeling function. Essentially, it is the label of, it represents the set membership over this continuous state space we have here, X. So the label that A holds if we're in this set, label C holds if we're in this set, etc. All right, so and we can think these things, these labels as just the indicators of this, the regions in the state space that we care about. We may want to enter them, we may start from them, we may not reach them, we may want to reach them, we may want to just do it in some order, etc. So we will represent the properties that we care in terms of these labels, and the labels will correspond to the set membership over the continuous state space. And this is going to introduce, essentially, if we take a trajectory that starts here at time t0, obviously none of A, B, C holds up until here. Now A is holding until this, nothing is holding, B is holding, nothing is holding, C is holding, and nothing is holding. Along the trajectory, we can then introduce what we will call the discrete behavior of a system, which is essentially the sequence of labels that we'll be holding along the trajectory. And then we will go and use a co-safe temporal logic specification, and then to grant these things a little bit more, we will have a final state, and we will have a finite time. All right. So that is the point, and the problem that we will try to solve. The model is given. The specification is going to be represented as a finite state deterministic automaton, and then Then we will try to compute a control law U that's going to minimize this, something over the continuous state and the inputs. And then we will keep track of the switches in the states of the automaton, and then we may introduce some cost of mode transition as well. And then at the final time, we will try to come to this final state that we care. And in addition to that, we want a discrete behavior of the system to satisfy the co-safe temporal logic specification we have. We want the discrete behavior to be in the language of this automaton that corresponds to the specifications that is given. So this is the question. We in the hierarchical control recording that I posted, we looked into a problem like this, and what we did was we took the continuous dynamics and then we discretized them to a finite state representation, and then applied the reactive synthesis tools or model checking or whatever the appropriate question that we're asking, and the tool from formal methods. Once we have the finite state representation for this site, we could go and check that against the given specification using an appropriate tool from formal methods. Here we will not do that. We will do something slightly different. So as you can see, once we compose these two systems, now we have a hybrid system. On the left we have a continuous dynamics. The U is to be determined, and then we have discrete modes on the right-hand side that will keep track of the evolution with respect to the underlying specification. And what's going to happen is we will search for a dynamic programming-based solution for this problem. Essentially, we can introduce this thing called VBStar. It is the optimal cost to go subject to the specifications. And what we will do is, while the labels remain constant, and then we will also separately look into our discrete transitions. So when the mode of the system stays the same, so we enter the region of interest, and while we are in that, we will impose a condition like this. We want the U that we are looking for to minimize this expression here. And mode transition here corresponds to, now I am leaving one region. The labels are changing. When the labels are changing, we want to transition to a new mode that minimizes this expression here. And then the quantification here is over what discrete mode we are in and what the corresponding underlying continuous set of continuous states are. And similarly here, what the discrete transition that we are taking and over what continuous states this is happening, and we also impose this at the terminal state that we specified. We want this V star to be less than 0. So if we can find a V star that satisfies all these, then we will have a solution for the problem. And this is by itself pretty complicated problem. Instead of that, we will go and now relax these things, and we will look for a approximate value function that is going to be an underestimator of the actual value function. Instead of we try to find the optimal value function, we will find an under approximator for that. And the conditions for searching an under approximator, this is the original condition we had in the previous slide. We will relax these things and look for this. It's a V that satisfies this inequality. And then at the same, when the labels are the same, when at the label switches, we will impose this condition, and the terminal condition again holds for its under approximator. And still, this is pretty hard problem, but this has relatively similar flavor to the conditions that we started looking into when we had a verification problem for safety properties. We are searching for a function V, and we want this combination, this linear map from V to be greater than 0 for all x's and u's and q, while these x, u, and q belong to some pre-specified sets. And similarly, we have similar conditions. So we are searching for V, and we want V to satisfy a certain property while we are in some set, or while we satisfy some other property, but these are similar conditions that we are trying to impose on the search of V. So they look much different and possibly more complicated, but at a high level, they are similar conditions that we had encountered in deductive verification for safety property example that we looked into. So I'm not going to get into how we can actually solve these things, but similar flow from, hey, I cannot solve this, here's a lower approximation, I cannot do it, let me go and search in some smaller family of functions, polynomials, quadratics, whatever, let me go and try to formulate as an optimization problem to try to solve it. If I can solve it, I'm going to go up now, I have a solution. If I cannot solve it, I don't know, just if we will need to go and improve one of these steps. All right, so this is that. And then once we have the V out of that, we can actually construct the control input that's going to achieve what we wanted to achieve. And this last piece is essentially saying that let's parameterize in some finite form and then go and try to formulate a control problem out of that. So let me just look at one little example. We have this continuous dynamics with A and B. So essentially we have x dot is equal to ax plus bu, and the cost function is from 0 to t x transpose x plus u transpose u dt, and then I believe this is the coefficient that we have for the mode switch. So just 1 times, I'm going to write it mode switch cost. So this is the relative weight that we put into mode switching. And then the specification is whenever we start in A, we eventually want to reach B. Whenever we start in C, eventually reach B, and eventually A, or eventually C. And then here's the solution. And then one thing that I will point to in the solution is it shows 2 different trajectories, starting from D and starting from A. Let's look at what happens when we start from D. So we are in the region B, okay? And starting from there, what we need to do is we actually eventually either reach A or eventually reach C. So we cannot go and converge to the equilibrium point. That's a terminal condition in this case. So eventually, at the end, we want to go to the state, but we can't just do this. We can't take this path to it. So we need to actually first, starting from the region B, we need to go away from it, either to A or C. And the trajectory does that. It first goes to A, and now once it goes to A, it says, okay, now I can go back, and it starts to go back. And the thing that we need to notice is both of these points are in the region B, but the underlying system actually behaves relatively differently. When we are in this region at this point in B, it pushes us away. And then once we actually go and visit A and come back, now the system remembers, because we have been keeping track of these modes, right? Now the system remembers, okay, I'm coming from A now. There is nothing wrong with me going and now terminating at this x is equal to 0, right? So this is essentially what this keeping track of the modes through this product construction between the underlying continuous dynamics and the discrete modes brings to us. And if we look at the closed loop dynamics within each mode, we will see that when we start here, we actually correspond to this mode in the discrete transitions in the finite state automaton. But when we come to region B again, we are now in this mode. And indeed, in the same region B, when you are in mode Q4, this continuous dynamics is stable. But if you are in region B, but in mode Q0, the dynamics are actually unstable. The closed loop dynamics are unstable. So this is how to interpret the results. And it is going to generalize to any underlying dynamics, so any underlying specification that belongs to the class of safe temporal logic specifications. Okay, now a little summary of deductive verification and synthesis techniques. So we typically start with a system theoretic question: is my system stable, safe, satisfies some temporal logic specification? And this is a question over the behavior of the system, right? Just we have a state space and how my system behaves in that state space. We transform it to a search for an algebraic function that will witness the satisfaction of the system theoretic property. It could be, depending on what we are asking, Lyapunov function, barrier function, value function, whatever. And this has nothing to do with the underlying system. It is just some conditions on a function of B that we are searching for, right? Given the dynamics, given the sets that we have, it does not even know that there is an underlying system anymore. And if we can answer it, there is a solution. And this is hard to answer, and therefore we try to translate these things through certain relaxations or equivalences, etc. We try to translate this into an optimization-based search or construction for these witnesses. And depending on what kind of dynamics you have, what kind of question you're asking, and what kind of tools that you might want to use, how you represent these underlying functions, etc., we might end up using different optimization routines or interfaces to optimization routines. On control side, obviously convex optimization have been used very heavily, but if the underlying dynamics are piecewise affine, and if you are searching for piecewise affine certificates for these properties, there's nothing wrong with going and trying to invoke and try to use an underlying SMT solver for search of these things. And this actually opens up the deductive techniques that typically had been invoked on the control side to actually pretty interesting problems. There are increasing examples, for example, on the underlying dynamics are piecewise affine, and we have a neural network that has piecewise affine nonlinearities, so-called Rayleigh nonlinearities in the neural network, and you can take the closed loop dynamics between them, and the resulting thing is going to be a humongous piecewise affine representation, and how you can ask similar verification questions. Conceptually, very much possible. The computational limitations that's probably the research where the field needs to think a little bit more. Okay, this is where I'm going to stop for this recording. Thank you for listening, and I'm happy to discuss these things over the course of this program.